All right, we did, what do we do? Area between two curves, the last two sections. This is volume by cross sections. This is one that some of you might not have gotten to last year. I told you to get through area of two curves. That was 11.1. This is 11.2. Actually, cross sectional. That's 11.4. Actually, sorry. Some of you didn't get there, but that's not a big deal. So I want to find the volume of a solid with known cross sections. So we have defined an integral, everything that we've been doing so far, as a way of a function to find the area, right? Area underneath the curve between the x-axis and the curve. However, there are other applications of this integral. One application is related to areas, finding the volume of a three-dimensional surface. And so one method we can do is what we call cross sections. They're two-dimensional cross sections that basically can be stacked on top of or next to each other to create a three-dimensional figure. So we can use the area between two curves to represent the base of the cross-sectional. So what I'm saying is, if this is our figure, okay, and this is delta y, so dy, okay, this is a dy, this is with respect to x, so this is a dx, and we'll go in this case. So the way this curve goes, so that means this square over here is going to be bigger than this square here because of the way the curve is. And then this square here is going to be smaller, right? And it's going to keep getting infinitely smaller with as close as we're getting to this particular point. And it's going to get bigger as we're getting to this point. Okay? And you can see the progress that's going. And that's where the width is your dx or your dy. In this case, it's the same thing. All right, I have my squares going from left to right here instead of from, I guess, top to bottom, or however you want to look at that based on your three-dimensional viewpoint. But that doesn't really matter. And so in this case, because I'm going in with respect to x, I'm going to go in here. Here's my x-axis right here. Okay, so what does that mean? That means that x is equal to a and x is equal to b. Those are going to be my two boundaries. Okay, so the area of the figure is going to be equal to, from a to b of the integral, a of x dx. And then for the cross sections for the perpendicular to the y-axis, that means they go perpendicular, okay, not parallel, so these are parallel. And if you want to talk about what we talked about last year, these are what we call vertical rectangles. We'll get more to this when we talked about discs method, the disc method, which is the next section. These are vertical, and these are what we call horizontal. Okay, it looks a little weird now because of the three-dimensional, but if I take this here and I just move it like this, and then I, make my curve like this, I'm making rectangles or squares that are parallel to the y-axis. Okay, that are parallel. Over here, okay, in this curve, I'm making rectangles or squares or whatever that are perpendicular to the y-axis. So that's what we call horizontal. Okay, so again, in this case, because I'm going perpendicular, I'm using the value of dy, so I'm going to go from c all the way up to d, which is where my integral comes from. Now, when we're finding the area of these shapes, these two-dimensional shapes, I have known geometric formulas for the area of a shape. Okay, so for instance, the square is s squared, right? The area of a square is s squared. The area of a semicircle, semicircle spelled wrong, is equal to half pi r squared. And then the equilateral triangle is root 3 over 4 times s squared. And so the s squared here for the square, basically what you want to do is, I'm not going to do this yet, we want to integrate s squared dx. So whatever s is, you want to plug in, whatever the side length is for the square, plug it in and square it and find the values from a to b. For the semicircle, the half pi, or the pi over 2, is actually a constant. So you're going to take that out front and go from a to b of r squared, or the radius squared dx or dy, whatever the thing is. And then for the equilateral triangle, I'm going to go from a to b, and then the root 3 over 4 is your constant that can be pulled out. and then this is s squared dx or dy, whatever. So it's always going to be whatever it is on the inside squared, okay, whatever the side length is squared, and then whatever constant is out front. So you have to memorize those constants. Obviously, they're not going to be given to you. You didn't get this far by thinking you were going to have everything laid out for you, did you? Nope. Just kidding. But seriously, you got to memorize them. Okay, let's go on to the first example here, which is find the volume of a triangular-shaped solid, triangular, whose base is the region bounded by the lines 1 minus x over 2 and negative 1 plus x over 2 and x equals 0. So what does this look like? Well, if I actually draw the figure, okay, x equals 0, so we know it's going to be starting there, or it's going to be bounded from there. 1 minus x over 2 is going to start up here, and it's going to come down, right, and keep going. And then this is negative 1 plus x over 2, so that's going to start up here, and then they're actually going to touch right there. They're going to touch right there. That's actually at the value of 2. You can figure that out by saying 1 minus x over 2 equals negative 1 plus x over 2 and solving it, right, and you get x equals 2. Okay, pretty easy. Easy peasy lemon squeezy. Okay, and I want to find that area in there. But in order to do that, let me erase all this stuff here. Okay, in order to do that, I got to figure out what I'm doing. I'm finding a square, so that's easy. Cross sections perpendicular to the x-axis. So the x-axis is here, so I'm finding a square that's going to be in here. Okay, a square that's in here and all the way up, right? I'm going to find an infinite amount of squares that are next to each other to find the area of that, and then that's where my volume comes in. All right, here we go. Okay, so, boom, let's do this. Square is s squared. Okay, that's pretty easy. But what is each of these? So if I find this square that's right in here, what's the base of that square? Well, the base of that square is the top function minus the bottom function. Okay, so the base of that square is 1 minus x over 2 minus negative 1 plus x over 2. So that's the whole length of it, because no matter where you are on this square, if you're right here, that's always going to be 1 minus x over 2. This here is always going to be negative 1 plus x minus 2. Okay, you're finding out the distance, right? Remember top minus bottom from the area underneath or between two curves? You're not finding area right now. I'm not like putting an integral with this, but you're finding what the distance is always going to be. This distance here is always going to be 1 minus x over 2. This distance here is always going to be negative 1 plus x over 2. And therefore, this is going to be 2 minus x when I condense it down. Okay? And now let's actually figure this out. So the integral is going to be from 0 to 2. Okay, that's where they intersect, from 0 to 2. Of s squared, well, that's 2 minus x squared dx. Okay? And you can do this a couple different ways. You can say, well, u is this, and I get u squared, and it's going to be this. Or you can multiply this out, and that's what, 4 minus 4x plus x squared. Okay, you can do that, and then take this dx, and then integrate that, and so on. And you can, I'm not going to do that for you. You can do that. You get around about 2.6666 repeated, okay, or 2.667 or 2.666. Don't write 3 6s. But anyway, that's that one. Okay, this one here, because we're using the same exact functions. Again, we're gonna have the same picture being drawn. Okay, it's the same picture being drawn. So this is gonna come down. This is gonna go up. This is gonna be at 2. This is at 0. Fantastic. But now the square cross sections are perpendicular to the y-axis. So that means my squares are going to go this direction. Okay? They're going to go in this direction. And so on. Oh, there are going to be infinitely amount of squares, infinitely many, infinitesimal, I don't know. I don't speak English very well. Infinitesimal or something like that amount of squares in that rectangle. I'm sorry, rectangle. Triangle. Dummy. Okay, and so what do I got to do? Well, I got to find the base of each one of those. All right. Well, the base. Okay. The base for, if you notice, let's back it up a little bit. If you notice, this is always, this line here is 1 minus x over 2. X over 2 is always going to be the base of the triangle because I'm going with respect to y here. This is with respect to y. Because I'm finding the area going this way, horizontal rectangles, or horizontal squares in this case. So this is always going to be that, okay? But, okay, I gotta find that in terms of y because I'm going on dy. But anyway, it's always going to be that. And then I'm going to get to this point here at 2, and then it's always going to be the bottom function, or that bottom line. And so I have to convert both of these functions into f of x equals, or I'm sorry, into x equals, because I'm doing it with respect to y. So y equals 1 minus x over 2. I end up solving for this, and I get x equals 2 minus 2y. Okay, so this here is just for this top piece, and then I have this other base, which is y equals negative 1 plus x over 2, which is going to be x equals 2y plus 2. And then this is for the bottom piece. Okay, and what I'm going to have to do is I'm going to have to split my integrals, because one function, if I look at it, okay, one function from, where does that point? That's at negative 1, right? And this is at positive 1. From negative 1 to 0, it's only going to be this bottom function. And then from 0 to 1, it's only going to be that top function. So you're going to have to split your integrals up. You got to kind of think about this a little bit. So negative 1 to 0 of the bottom function, which was 2y plus 2. I'm going to square that, dy. I'm going to add in the integral from 0 to 1 of 2 minus 2y, square that, dy. Okay, and what am I going to get? Well, I already found the area over here with respect to x. Well, now I'm doing it with respect to y. So I'm hoping I get the same value, and you basically do. It's around 2.666 repeated, or 2.667. Okay, it's the same thing. You should get the same thing no matter what. That just goes to show you that no matter which way you do it, you do get the same thing, as long as you interpret the function the way it should be interpreted. If you used x's here, okay, instead of y's, that's not what they're asking. Right? Perpendicular to the y-axis is using in terms of y. Okay, we got to remember that. So rectangles of h equals 4 perpendicular to the x-axis. Okay, rectangles. So I have, again, the same function. Okay, it's the same thing. Boom, boom. This is 0, this is 2, this is negative 1 and 1, right? And what is the base of the function? Well, we already found the base of the function, okay, is always going to be this. Whether it's a rectangle or whether it's a square, it doesn't really matter, right? A square is a rectangle. So we can, hopefully understand that. So the base is going to be 2 minus x. That makes sense, hopefully. Then the height is 4. Height is equal to 4. Well, how do I find the area of a rectangle? Okay, well, it's base times height, right? So I'm going to take the integral from 0 to 2, because these are all in x's, of 2 minus, I don't care, I'm going to do that. 2 minus x times 4 dx, okay, which is the integral from 0 to 2 of 8 minus 4x dx. You can integrate that, you can solve that, and you're going to get about 8. What does that tell you? That probably shows you that it's probably not that accurate, right? Rectangles are probably not that accurate, all right? Just be aware of that. Rectangles where h of x equals 4 minus x, perpendicular to the x-axis. So in this case, Our height is 4 minus x. Okay, 4 minus x. So again, we're going to take the integral from 0 to 2. We already knew the base of this rectangle, which is 2 minus x. So base 2 minus x times the height, which is 4 minus x dx. So that is equal to the integral from 0 to 2 of, you can multiply that out, right? That's 8, oh man, minus 6x plus x squared. That sounds about right. I think that's right. Dx, and this is going to be about 6.667. Okay, I think it's 6.6 repeated, but I just want to round it there. Okay, again, it's getting smaller because now the height is going to change with respect to the base. Okay, here is the height is stagnant. The height is staying the same at 4. That's not very good. Semicircles. Let's go. Let's make some semicircles. So, what do I know? I know that if I have my drawing, I'm so good at drawing. This is 0, this is 2, -1, and 1. If I want to make a semicircle, okay, what do we know about semicircle? We know that the formula is pi over 2, okay, 1/2 pi r squared, right? And remember, it's pi over 2 times the integral of r squared dr, or dx in this case, so we just change r to x's. I got to find the radius. Well, since I know that the base of the function is always going to be 2 minus x. It's always going to be 2 minus x, right? We talked about that before. This base is always going to be 2 minus x. Well, in this case, if I make a semicircle with the base is 2 minus x, so like if I made a semicircle every single time, this is the diameter. So I got to take this and divide it by 2. So it's 1 minus x over 2. So 1 minus x over 2 is our radius. Okay, I'm going to use that in the r piece here. So I get pi over 2 times the integral. The integral is still from, what, 0 to 2, because we're still perpendicular to the x-axis, of 1 minus x over 2 squared dx, which is about equal to pi over 3. Or 1.047 rounded. Okay, you can do that math. All right, so that's that one. Let's do some isosceles. I don't think we know how to spell isosceles. That's crazy spelling. Autocorrect apparently in Microsoft Word doesn't autocorrect very well. An isosceles right triangle whose leg is bounded by the region and perpendicular to the x-axis. So again, I'm going to have the same region. Okay, boom, boom. That's a terrible drawing. I am so very sorry. I thought I was doing better. I'm not, actually. It's now 12:30 a.m. on New Year's Day. -1 to 1, 0 to 2. Okay, so how do I do this? Well, we know the base is 2 minus x. That's pretty similar, okay? They're all going to be the same, right? So this is our base right here of this triangle. Well, the height, since it's an isosceles triangle, the base and the height are going to be the same. So the base and the height is also 2 minus x. All right. Then, what do I know? What do I know? So an isosceles right triangle, you got to remember this is a little bit of a math problem. So this is one that I don't know why this wasn't up here, but I'm going to add it up here. So an isosceles, oh, there we go. Isosceles right triangle is 1/2 s squared. Okay, 1/2 s squared. All right, so that makes sense there. So let's go back down. So 1/2 s squared, okay, with the integral, that 1/2 can be pulled out. The integral is from 0 to 2 because it's perpendicular to the x-axis, so 0 to 2. And then 2 minus x and 2 minus x. Sorry, I'm watching a football game. 2 minus x is both the same, so squared dx. Okay, and sorry, I was looking at something else. You can figure that out. I'm not going to figure that out for you. It's going to be about 4 over 3. 4 over 3. Okay, 4 over 3. So that's isosceles right triangle whose leg is bounded by the region. So if I make a triangle in here, okay, I'm not going to really do it, but this figure, this base piece, this is the leg. So this is the leg. In letter G here, I'm going to have the same exact figure, but the value here is the hypotenuse. So technically, like, I'm going to make triangles that look like this, okay? So the value between the upper and lower functions, so we know the hypotenuse in this case, not the base. The hypotenuse is 2 minus x. So we know that. That's true. Okay? And so what I got to do is I have to find, so here's my triangle. Here's my right triangle. We know this is 2 minus x. I need to find these values here. Okay? I need to find those values because it really doesn't help me trying to find the area of a triangle. I guess I can find the area of a triangle with I know the hypotenuse, but you know, it makes it a little bit more difficult. So we got to do some math. So back in geometry, I don't think you'll have anything this difficult on the actual AP exam, but you could, I guess. Back in geometry, we talked about similar triangles and right triangles and a whole bunch of right triangles and 45-degree angles and stuff like that. So we know this is a 45-degree angle. This is our right angle here. And now I have, this is 1 root 2 as a 45 degree. So this is our base one, okay? 1 root 2, like 1 squared plus 1 squared is equal to root 2. Or, well, 2 square rooted, yeah, root 2. And so then I can find out the length of the a value, or the legs, by making simple ratios. So a is to 1 as the hypotenuse is to root 2. And so then if I solve this, I get a is equal to h over root 2. Well, what is h? We know h is 2 minus x, right? So, we can do a whole bunch of different things, but now all of a sudden I want to do this. We know the area is equal to, of an isosceles right triangle, okay, the area is equal to half then the side squared. All right, and well, what is the side? We know that the side is going to be h over root 2. So we're going to take the integral, that 1/2 is going to pop out, okay, of the integral h. I don't want to do that yet. Sorry, I don't want to do the h yet. I want to show you where I'm getting that numbers from instead of skipping some steps here. Okay, so we got 1/2 s squared, which is equal to 1/2 times h over root 2 squared, which is equal to 1/2 times h squared over 2, which is equal to h squared over 4. Okay, h squared over 4. And so now I'm going to use this. Okay, I'm going to use that to find the area of that isosceles triangle. Okay, my area was this, but it got manipulated because of the h value. It got manipulated. And so that 1/4 is going to be popped out from 0 to 2. Well, what is h? H was 2 minus x. 2 minus x squared dx. And then I'm going to integrate that, and I get about 2/3. Okay, I get about 2/3. That's a fun one. You probably won't have anything like that on a test or the AP exam, but I don't know. It's fun. It's fun. This video is really long. I'm sorry. It is what it is. Medium eraser. Medium eraser. Medium eraser's not big enough. I need a large eraser. Maybe I need to petition Microsoft to get a large eraser. Okay. Equilateral triangle perpendicular to the y-axis. Again, I have my figure. All right. Oh, my football game's over. Okay, -1, 2, 1. And because I want equilateral triangles, so I'm going to go this way. Okay, these are my triangles here. These are my triangles here. Equilateral triangles perpendicular to the y-axis. That means that I need to turn these f of x functions into f of y. So we know y is equal to 1 minus x over 2. So therefore x is equal to 2 minus 2y. And then the other one, which is the bottom function, is equal to -1 plus x over 2, which turns into x equals 2y plus 2. Again, you're going to have split integrals here, because from -1 to 0, it's only this function. It's only this function here. Then from 0 to 1, the top function takes over. Okay, so you're going to have to split integrals. So equilateral triangle, let's see if I can go back up here. It is √3 over 4s squared. So that's what we're going to use. Okay, so we're going to go √3 over 4 from -1 to 0 of that function, which is 2y plus 2. Ooh, I don't know what the heck that is. That was crazy. I don't know what that one was. That's crazy. 2y plus 2. We got to square it because it is s squared. dy plus, now the integral from 0 to 1. Again, we have that √3 over 4 there. Sorry, I forgot that. Of 2 minus 2y squared dy. Again, you can do the integral. You can do u substitution and take out a half. To each of those, this would be a -1/2. I'm not going to do that. You can do that. If you need help, talk to me, but you should be okay. And you're going to get around 2√3 over 3. Okay, around 2√3 over 3. I don't know what that decimal equivalent is, but that's fine. If you want to round it to the third decimal place, that's fine. Okay, this video is really long. I am very sorry, but it is what it is. There's a lot of examples, and we have to go through each different type. So I will see you on the next one. Deuces my gooses.